You expect modern trains to be better in every way, but one 80-year-old steam locomotive can still pull more than its successors and outlast and outperform them, at least in the critical areas that count most to railroad crews. With a design meant to conquer the fiercest climbs and the harshest climates, this machine's raw torque and mechanical resilience and its 80-year track record have never been fully matched. How did a wartime giant surpass the smartest technology of today? And what does better really mean when we compare them side by side? Union Pacific's Big Boy was never designed for ordinary duty. In 1941, at the height of World War II, the railroad ordered a fleet of 25 steam locomotives from the American Locomotive Company, each one built to a 4884 articulated wheel arrangement. This meant 4 leading wheels, 2 sets of 8 driving wheels, and 4 trailing wheels, all connected by a flexible frame. The goal was clear: move enormous freight loads over the steep grades and long distances of the Wasatch Range between Ogden, Utah, and Cheyenne, Wyoming, without relying on helper engines or electronic controls. Each Big Boy measured over 132 feet long and weighed more than 1.2 million pounds with its tender. The driving wheels alone supported 540,000 pounds stuptions, translating to a starting tractive effort of 135,375 pounds force, enough to set a 4,000-ton train in motion from a dead stop on a 1.14% grade. The boiler operated at 300 pounds per square inch, feeding 4 massive cylinders that delivered power directly to the rails. Durability was built into every detail. The design philosophy favored overbuilt frames, redundant safety systems, and mechanical components sized for continuous punishment. Crews could expect to run these engines day and night, in all weather, through the war years, and into the post-war freight boom. Each Big Boy logged over 1 million miles in revenue service, often running 160 miles per day. No computers, no sensors, just raw mechanical force and human skill. This approach to locomotive design prioritized survival and output above all else, setting a benchmark for what a steam engine could accomplish when pushed to its limits. Defining what makes an older locomotive better requires a clear set of criteria. In this analysis, better refers to 5 specific areas: raw pulling power from a standstill, mechanical resilience under stress, reliability in extreme environments, longevity of operational life, and simplicity of field repairs. These are the domains where steam locomotives from the 1940s, such as the Union Pacific Big Boy, demonstrate advantages over modern trains. Claims about higher top speed, better fuel efficiency, or lower emissions are not part of this comparison. For context, a Big Boy under full test conditions could consume up to 11 tons of coal and 12,000 gallons of water per hour, numbers that highlight the trade-off for brute force. Modern locomotives far surpass steam in efficiency, running costs, and environmental impact. However, in situations where maximum torque at 0 speed, rugged construction, and the ability to keep moving through failures matter most, older designs set standards that remain difficult to match. The focus here is on how these steam giants perform under punishing conditions, not how cheaply or cleanly they operate. This approach keeps the scope narrow and avoids confusion with areas where technological progress has clearly moved forward. The comparison is about survival, repairability, and sustained output under stress, not about which machine is more advanced or economical in everyday service. By establishing these boundaries, the evaluation can remain fact-based and credible, setting up a direct look at each of these 5 superiority metrics in the sections that follow. Big Boy's advantage begins where most modern locomotives struggle. Starting a heavy train from a dead stop, especially on a steep grade, is where this locomotive stands out. The core of this capability is tractive effort, measured at 135,375 pounds of force for the big boy. This force is delivered directly to the rails through 4 massive cylinders, each stroke translating steam pressure into immediate motion. Unlike diesel-electric locomotives, which build their power curve as speed increases, steam locomotives like the Big Boy produce maximum torque at 0 speed. This means a Big Boy could set a 4,200-ton freight train in motion on a 1.14% grade, a feat that often requires multiple modern engines or distributed power systems. In 1943, dynamometer tests measured the Big Boy's drawbar horsepower at 6,290 at 41 miles per hour. The locomotive's real strength, however, was in overcoming inertia at low speeds, where traction matters most. Crews relied on this brute force to keep freight moving over the Wasatch Range without stalling or slipping, even when facing overloaded consists or challenging weather. The ability to apply such raw pulling power from a standstill set a benchmark for what heavy rail could accomplish, and it remains a defining metric, where 1940s steam outperforms today's more efficient but less forceful designs. Steam locomotives like the Big Boy were designed to be fixed anywhere, often with nothing more than basic hand tools and the ingenuity of their crews. Mechanical simplicity meant most failures could be seen, heard, or felt directly, with no diagnostic computers or proprietary software required. When a Big Boy slipped off the rails near Rawlins, Wyoming, the crew and track workers used wood blocks and jacks to ease the massive drivers back onto the track, a method that relied on teamwork and practical know-how rather than specialized machinery. In the shops, repairs went beyond routine maintenance. Pouring new Babbitt bearings for the connecting rods or machining replacement parts from raw stock was standard practice. Skilled machinists and boilermakers could disassemble and reassemble major components using lathes, presses, and welding equipment found in any heavy railroad shop. This approach allowed for quick field fixes and long-term resilience. Modern locomotives, by contrast, depend on electronic modules and diagnostic systems. A failed sensor or control board often means waiting for a replacement, sometimes sidelining a train for days. With steam, as long as there were tools, materials, and skilled hands, the locomotive could be patched up and sent back on the line. This repairability was essential for keeping freight moving through war, weather, and heavy use, and it remains a defining difference between 1940s steam and today's high-tech engines. Operating in the heart of winter demanded more than just horsepower. It required machines that could function when temperatures dropped below -30 degrees Celsius. Steam locomotives like the Big Boy proved their extreme resilience in these conditions, relying on physical laws rather than delicate electronics. The boiler, kept hot by continuous firing, resisted freezing even during long stops. Mechanical linkages, lubricated by hand, could be checked and adjusted on the fly. In contrast, modern diesel electrics often face cold-related issues, including fuel gelling, battery failures, and sensor malfunctions that can leave a train stranded until specialized help arrives. Big Boy crews worked through blizzards, shoveling snow from switches and monitoring the engine's vital signs by touch and sound, demonstrating hands-on reliability. During severe storms, it was not unusual for steam locomotives to keep moving while newer engines stalled, especially on exposed mountain passes. Even today, the 2019 incident at Blair Hill, where Big Boy 4014 assisted a stalled freight, serves as a reminder that these machines, built for the harshest conditions, can still deliver when the environment turns hostile. Union Pacific Big Boy 4014 returned to life in May 2019 after nearly 6 decades in storage, following a restoration that required 5 years of dedicated work. Craftsmen at the Cheyenne Steam Shop rebuilt the locomotive from the frame up, replacing worn bearings, machining new parts, and fabricating boiler components to meet modern safety standards. The process involved stripping the engine down to bare metal, inspecting every stay bolt and rod, and hand-fitting components that had not moved since 1959. Unlike modern locomotives, which are often retired after 30 or 40 years because electronics become obsolete, the big boy's mechanical design allowed it to be revived after 80 years. Its return to mainline operation is proof that well-built steam engines can outlast several generations of newer technology, given the right skills and materials. Each mile covered since 2019 adds to a service life that stretches back to 1941, a testament to the longevity built into these machines. Modern locomotives rely on complex electronic systems to manage everything from traction control to emissions. These microprocessors and sensors have a mean time between failures measured in years, not decades. When a circuit board or software module fails, the locomotive often sits idle until a replacement part can be sourced and installed, sometimes waiting days if the component is out of stock or obsolete. Maintenance planners track these electronic failures closely, as they account for a significant share of unscheduled outages in today's fleets. Steam locomotives, by contrast, use purely mechanical controls and linkages. Their design tolerates rougher track conditions and minor defects that would trigger safety shutdowns on modern engines. Where a big boy could keep moving over rails with worn joints or uneven ballast, a diesel-electric's electronics may demand tighter tolerances to avoid faults. This difference in system resilience means that even after 80 years, steam's simplicity can outperform advanced technology in environments where reliability and ruggedness matter more than efficiency or speed. Today, engineers still study these locomotives for lessons in durability and adaptability. As rail systems grow more complex, the value of proven, resilient design only increases. Sometimes progress means knowing what to keep, not just what to change. What do you think still sets these classics apart? Join the conversation below.